Oh!
Ongelooflijk, dat er iets gaat doorkomen. Dus ik ga hem hier nog even stoppen.
Normaal gezien zou het hier nu moeten live zijn.
Minimaliseren. Ik ga nog een keer even kijken. Ik zie al een opname. Ah, goed gelukt. Dus ik ga hem hier best aandoen. Dat is wel moeten werken. Er komt er ook vertraging op zitten. Hè?
Ja.
Dus je moet niet vergeten om de startpunt te doen.
Althans, alles brandt.
Ah, er is nu een nieuwe livestream, 2 minuten geleden. Blauw scherm. En je blijft maar laden. Dat was het normaal. Meestal wil je veel rapper beeld daar.
Is dat nogthans goed?
Ja, wat ik zeg, alles staat naar de hand. Snap
Van
het
nu
dan?
brandt het allemaal. Hè?
Ja, ja, dat is dat.
Je zegt zelf dat je live bent.
Ja. Spelen. Ik heb geen beeld en geen geluid. Kan ik hier? Ja, we kijken.
Broadcast in progress.
Kijken wat het probleem is. Ah, nu hoor ik wel. Broadcast progress, dus ik denk dat hij nu aan het...
Ah, ja. Is het live?
Heb je hem nu nog een keer opnieuw opgestart of heb je ondertussen al gestopt?
Ja. 2 minuten geleden.
Ja.
Nu streamt hij. Normaal moet je af en toe mijn hand zien. Ja.
Heb je gekeken of dat ik nu in beeld zie? Daar is de hand. Oké, nu ga ik mijn één kant. Normaal toen mijn hand zit, staat er ook aan.
Ja. Ja, daar is hij.
Wat was het?
Dat is een comedy show. Zo zijn, veel plezier.
Voilà, dankjewel. En als je verveelt, je kan weer kijken.
Op mijn fiets ik heb zo een houder gekocht om mijn gsm in te steken en kunnen zelf op pad naar huis.
Ja, oortjes in en luisteren.
Allee.
Veel
plezier, veel
Ik ga eerst beginnen met het blaadje uit te delen. Ik ga dat zo dadelijk vertellen. Dus vandaag, het grootste deel gaat eigenlijk over statistische testen. Maybe I'll switch to English. I forgot. So, most part of today will be about statistical testing. And there are quite some tests that I'll discuss. But I do not expect for you to know all of them, at least by heart. So this is what we call a cheat sheet. And you can also use this on the exam. So this will just tell you, based on if you can look at the data set and see what variables are being used in the data set based on this table, you should be able to decide which test you should perform. Okay? This one. So by just looking at this table, you should be able to decide which test to use. And now you will see for most of the tests, it's actually just one line of code in R. So it makes it quite easy. So the most difficult thing is look at the data, see if it are nominal variables, measurement variables, or rank variables, and then with this table decide which test to do. So this is what I will explain today. So let me go. First, also take our recording. Let me first go to our learning environment. So today I will first give us a short overview of the last part of data analysis and visualization. So I did not yet discuss the part about dimensionality reduction. There's also one exercise to do here. So I did not publish, but for the other previous exercises you should now see exercises 1, 2 and 3 and 4 are being published. So this is actually the R code. If you load it in your RStudio, you can just see the solution of the exercise and also execute, and you can compare it then with what you tried to do, if it's exactly the same or not. And if you have any questions, just send me an email. So by the end of this week, then I will also publish exercise 5 and exercise 6, and then next week I will publish exercises 7 and 8 from the chapter on statistical testing. Okay, so let me now move to the chapter of dimensionality reduction. So in the previous chapter you saw that you, based on a number of variables, you can try to visualize the data using 1 or 2 variables, or even maybe 3 variables. For example, if you would do it in 3D or with a bubble chart, well, the third dimension is what we call the bubble dimension, but you have more than 3 variables. It's difficult, first of all, for our brain to have a look at that kind of information. So what you can do is you can use the technique of dimensionality reduction. If you would have tens or even hundreds of variables, you can actually try to reduce this high dimensional data and try to visualize it in 2 or 3 dimensions, so you can actually look at the high dimensional data. This is what this part is about. So many variables, many features, so we are talking about high dimensionality, and then this is a technique where you can project the data into space with less dimensions, which limits the computational complexity actually, and you can actually visualize it. There are 3 techniques that I will show you an example, more exist, but I will show you MDS, PCA and TSNE, and you can divide them actually in 2 types, in linear methods and non-linear methods. So for example, the MDS, the first one that I'll discuss, is a non-linear method, and then the PCA, the second one, is a linear method. And this is just if this would be the data, only 2 variables in 2 dimensions, and we would have to make a distinction between these data points. You could say, if it's linear, that this would be maybe one group and this would maybe be one group. So this is linear. But you could also, if you look at this one, say, actually, these are similar data points. And then the other ones outside are another type. So this is then if you would use a non-linear method. Or if your data points would be like this, you could draw a line here, and then the linear method would say these are more similar and these are more similar. While a non-linear method could make something like this, and then these data points above the dashed line are similar and those below. So this is what it actually is doing with your data. And this is from a publication where you see more different methods on the same data, what they perform and what you're actually doing with the data. So the take-home message is actually, when you have a high-dimensional data set, it's good to try different methods and see where you see certain groups. For example, in many cases you would try a linear method and you would try a non-linear method. So multidimensional scaling is a visual representation of the distances actually. So if more If the objects are more similar, then you would say they have shorter distances. While else they have longer distances. So let's say we have a patient data set and would have 3 variables to make it easy. Let's say the age of the patient, the height of the patient, and the weight of the patient. If these are similar, let's say you have someone of age 25, 1 meter 80, 75 kilograms. Then you have someone who is maybe 24, 1 meter 82 and 77 kilograms. That's actually close together, right? If you could compare that with a person age 85 of 1 meter 65 and weighing 120 kilos, that will be a longer distance. That's actually how you should think about this. That's now only 3 variables, but the computer is actually able to do that with hundreds of variables. And in R, you can do that by using the dist function. This will actually compute this distance. So compute the distances between the rows in your data matrix. So one patient then could be one row with several variables, and it will compute the distance between those rows of information. There are different measurements that you can do. So you can, for example, say I want to use Euclidean or Manhattan or maximum or some other ones. Of course, you should not know the formula. This is just as an illustration. Euclidean distance would mean if this is the axis and this is one data point and another one, this is actually how the distance would be calculated in Euclidean space here. And this would be the formula. So you don't have to remember this formula. And then there are other methods of calculating distances between data points. This is an example of the iris dataset of the flowers, where you then actually here calculate the distance. Now it's important that you notice here, what does this mean? These square brackets, which kind of data type is this with the square brackets? Remember how we call this? A data frame, remember? And then with a comma, you have before the comma are the rows, indeed, and after the columns. So in this data set, if I remember correctly, I have 5 columns actually, but I'm only selecting those that are numerical. Okay, so the calculations of petal length, sepal length, petal width, and sepal width, I think. So species is not included because that's a factor. So we're only taking numerical variables, the measurements actually. And then you can, this calculates the distance, then you have the new coordinates, and then you can actually make a plot. So then this is actually using the multidimensional scaling, which you calculated with the distance. So the default is Euclidean. If you plot then those data points, you will see 3 groups, the ones in blue, the ones in red here, and then the ones in, let's say, purple. Those are a bit close together, but there's a clear distinction with this group. These are actually colored by species, which means, indeed, for each species, those 4 variables make a distinction between these groups. So those 4 kind of variables, we can actually reduce that information into 2 axes, 2 coordinates. So from 4 we go to 2. So we reduce the number of dimensions. If you would want to use another distance method, you could specify here the method. So in this case, if you would use the Manhattan distance, you just add that here, then you can do just the same, and then you will have a plot like this, which is actually similar. So that's the MDS method. The other one is PCA, which is a linear method. And then, for example, if this would be 2 axes here, then what you actually will do is you will try to identify new axes which represent where the data has the most variance. So in this case, if these would be 2 new axes, you would see here 3 points, here 3 points, 3, and then here 2. And that would divide actually with the most variance in these data points. So this is then what you get new, what we call principal components. And to get these, we're not using the this function now, but the default in R is PRComp. That is one function you can use. There are other ones. So for example, if you use the bioconductor, this is another one you can use to calculate these principal components. How do we do that in R? As an example, here we have our PRComp on the data, and this data has been log transformed. You can also center and scale. So you can center, scale, and sometimes log transform to filter off trivial effects which you could dominate the PCA. Why is this? For example, let's say if you would have one variable, so we have variable 1 and we have variable 2. Could we, let's say that your values are here 2, 4, and maybe 10. So this is actually 5 times, right? But there's a big difference if you would have, let's say, 20, 500, and 10,000. Okay? If you would keep it like this, this would be minimal. 10 means nothing. You compare it with these. So what we do is, for example, we use scale, which actually means we will reset that between 0 to 1. And this also between 0 and 1. We will rescale. And then all the values will be between 0 and 1, and that's better to compare them. So this is using, for example, scale, so you can scale, center, and also sometimes it's useful to do a log transformation. And then in this case, you can have a look at what the result is by plotting the result of the PCA calculation. I use type line here. And then you see here actually, this is then the variance, and this is the component 1, 2, 3, 4. You actually see that the most variance is in component 1 and 2, so then it makes sense that here you plot component 1 and 2. This is actually what you're doing. And then this is in this case the result, so it looks a bit similar as with the MDS method, right? You get these kind of flowers closer together as a group, and then the other ones here. Even a bit more overlap. So for this data set, I would say that maybe it's even a bit better the results with the MDS method. You could also use the third one in 3 dimensions. So if you use the library RGL, compute again, and then not using only the first and the second, but also the third principal component, you could actually render it in 3 dimensions and then rotate it, and sometimes adding a third dimension makes you see another group of another distinction. If you would have, let's say, some overlap here, in these 2 dimensions, it could be in the third one, in and outside the board. Remember that the red circles are maybe here in front, and that the purple ones are more at the back. But if you look at it from the front, they are overlapping. But if you turn in the third dimension, you could see that there actually is a distinction between them. So it can be useful to also have a look at the third dimension here. And then the third one is one that is getting quite popular and often used. Also, for example, people using single cell sequencing data like to use this method. It's called TSNE, or T-distributed stochastic neighbor embedding. So this is also a nonlinear dimensionality reduction algorithm, and that can find actually some patterns in data. And this is even better on really huge data sets. For example, lots of information of single cell sequencing. If you want to have a look at all that information, this is really a very good method to do that. So you can actually identify or observe clusters in the data. But it is important to remember that it is not a clustering algorithm. Just by reducing the dimensions, you will get a number of clusters. And they have a number of parameters that you can take into account. And one is the perplexity parameter. And then here you see, this is from this website that I took, you can see the difference between the perplexity values. And in most cases you get good results by using 5 to 50. Ranging from 5 to 50. So in this case, 5, 30, and 50 in these three cases, you can clearly see the two groups of data points, which would be like this in the original data set. Also here. This is then with the steps changing. So with this method, it's a good idea to try out a few perplexities, maybe 5, 30, 50, and have a look where you get nice clusters. But in this case, for all three, I think it's obvious that you can identify the two groups of samples, for example, in this case. And then this is actually an example on count data. So I just, what I did is extracted a smaller data set, 2 cell types of 8 patients. So these are actually the 2 cell types of the 8 patients with information of 2,000 genes. So which means we actually have, this then would be 16 columns probably, and 2,000 rows. So you can have a look at that here. So that's a really large data frame already. And then if you use this for the TSNE method, then you will see normally here that the variances are much, much larger, so very good results, and that you can normally see them, the different clusters. So what I did here between these two is just the scale here is different. So if I have a look where the difference is, here I just changed the limits of the x-axis and I changed the lower and upper limit of the y-axis, and that's then you can nicely see the 2 cell types. Actually, this is the C cell type and this is the I cell type. Which means even if there are 8 different patients, you would say 2 samples from the same patient would cluster together. This is not the case. This just means that that cell type, it doesn't matter which patient it is, you can still identify. So the different patients, that specific cell type has the same expression. And that's actually why these are clustering together here. The exercise is one from this publication where they used, I think, 25 different tissues of 1,641 individuals. And it's a nice example to repeat actually this experiment. Now this is lots of data, it might take a bit of time to load and to calculate, but you can do it on your laptop, just have a bit of patience. And you should filter only 3, that makes it a bit more doable. So this is the complete data set, which is in one of the R dataset zip files, I think. And then you first make a subset, which we saw in one of the previous chapters, and only try to use these 3 cell types. So you have to actually use the information in the sample labels to select these 3 clusters. And then you can get a result something like this. So this is, for example, a TSNE with a perplexity of 10. You clearly see these 3 cell types or tissues. And also with the MBS method, you get a very good result. That's it for the multi-dimensional scaling, PCA and TSNE, so dimensionality reduction techniques. No questions? Maybe they'll probably come later. So if you would have a problem, just send me an email or ask in the discussion forum. And then by the weekend, I will also publish the example exercise or the solution of the exercise. So that was PowerPoint 5. And then we'll switch to the statistical testing. So maybe I'll just switch on the light in the back. Yes. Just have a look. Is my recording? Yes, it's still working. So for the statistical testing, I also added for this first presentation some movies here. So some movies from the day course, only from the first chapter of statistics, but I also added here of some concepts. You can also read more here if you want to know more about that. But that's just optional. So maybe you already know some statistics, or you probably had that somewhere in your previous studies, I guess. So if you want to do statistical testing, you always define a null hypothesis and an alternative hypothesis. For example, it could be, we assume that water boils at 100 degrees. The alternative hypothesis would then be that it does not boil at 100 degrees. So that could be one null hypothesis and alternative hypothesis. And then this is another example. For example, of knee surgery patients, normally we expected the recovery to be 8.2 weeks or less. And then here they try the alternative, and then if you would change the physical therapy, the alternative would be that actually it is greater than 8.2 weeks, so the recovery period. That could be another one. So what you want to do is, if you do the hypothesis testing, if you determine the two competing hypotheses, the null and the alternative, you set your level of significance, which we call the alpha. So this is significant, this is highly significant. So some people use the 0.05, but for example, if we are looking at RNA sequencing data, we want to have genes that are upregulated, downregulated. Normally we take highly significant genes. So we use this then as the cutoff value. Then you calculate your test, and then the result of your test is that you will also always get a p-value. And then your p-value, you compare it with this, and then you can decide if I should reject the null hypothesis or not. And actually this is then to show you how this works. So if you would make a distribution of your data, this is a normal distribution, this is where most of your data points are, and then this is actually the chance that you have it here is quite exceptional. And this is here the rejection region, what we call. So this is actually, depending on what you choose as an alpha value, 0.05 or 0.01, the area in the tail also. So if you reject it, it's here, and if you fail to reject it, your null hypothesis is normally your data would be here. And then this is what we call the Z value or the critical value. And then sometimes you probably have heard they talk about one-tailed tests and two-tailed tests. So the difference is, this would be an example of one-tailed in one direction, where you only would look, for example, at this one, or only look here. If you have a two-tailed test, actually you are looking at these two to reject. So this is then the example where it is different than the mean in this case. These are the different values, the guidelines, but normally we do not look at these. Normally you have a look at the p-value below or equal to 0.05, which is significant, and in many cases actually we look at highly significant p-values below 0.01. This is to show you how you can calculate the Z value. Should not remember the formula, I won't ask you the formula. This is just an example to show you how you can get to this Z value. So this is 1 times the standard deviation, and this is 68% of your data. 2 times the standard deviation is 95%, and if you go even further to 3 times, it's quite exceptional. That's actually 99% or even more of your data. So then you have a very, very small tail. And then here you can get, in this way, if you calculate, you can get your Z value. This is an example to show you how this is calculated. If you use the formula, then you get a Z value of 2.72. So the standard deviation from the mean, and then you can actually you can look in a Z table to see what the p-value is. So this is illustrated here. So if we calculate it in this example, the Z value of 2.72, we look into our Z table, and then we see 2.702 gives us a value of 0.4967 in our Z table. That's this value. And we are looking in our Z table, we are looking at this part here. So which means if this then would be 0.4967. To get this value, we have to subtract it from half, which is 0.5, and then the result is 0.0033. So in this case, this is then our p-value, and this would be highly significant in this case. So that's the introduction. Now I will go over the statistical tests one by one. So that's actually what the next of this chapter will be, and also the next two chapters. The different statistical tests. And you can look at this table then to help you with that. Maybe just show you for the people at home also where you can find this. So if you go to the modules on the learning environment at the bottom, I provided supplemental information. And there also you can see here the R-stats cheat sheet. So that's this one here, this table that you can use on the exam also to decide which test to do. And then of course you should be able to look at the data, decide which test to use using this table, and then perform the test in RStudio. These are for next chapters. I also already provided some cheat sheets for you. If you already want to have a look at the, what I asked on the exam, this is the example exam of last year if you want to have a look at that. That's also available in the supplemental information. This is to show you what the difference is between what we call parametric tests and non-parametric tests. So for parametric, you assume a normal distribution, so the one I just showed you. If your data is not distributed normally, then it's better to use a non-parametric test. So the most important thing, if you have data and they ask you to perform a statistical test, you look at the normality and you look what kind of variables you have. So normally you will have measurements, numbers, something you measured in an experiment. That's one option. The other option is nominal variables. What is this again? Nominal variables. What could that, for example, be? A nominal variable, categorical variables. Then we're thinking about factors in R.
That's a string.
A string, yes, could be male, female, red, green, something like that actually. Or maybe disease, healthy, could also be. And then ranked variables is just that this is the first one, this is the second one, this is the third one that you have a ranking. That's also possible. I'll show you, I think, two examples of that. This is just to decide, based on the distribution, which kind of test, for example, you can use. And then maybe have a look at the first series of tests. This is just an example of an experiment they did with giant isopods, showing here. So you probably know this isopod when you turn over a stone and you see all of these crawling. Normally they're only this big, but the giant isopod, as you can see, actually this large. So they did an experiment with that. So you can measure, for example, the head of the isopod. So this is a measurement variable, and you could compare males and females. So if you would then have to look here, then you will see here nominal variable 1, measurement variable 1, because male, female is a nominal, and measurement, the width of the isopod head, is then your measurement variable. So then you see in your table that you end up with a 2-sample t-test, right? Or one way ANOVA. Another thing you could do with this data set is you have different genotypes. And you could compare the frequencies of the genotypes. This means you only have one nominal variable, so then you look at the exact test in the table. One nominal variable, it's an exact test. And then the third one is what they did, and what they could do is you could shake them up, these giant icebergs, and then roll them. And then they crawl like this. And then just you say, ah, that one unrolls first. That one unrolled the second. That one unrolled the third, and so on. So you make a ranking. You compare the unrolling. This could be then a ranked variable. Then you look at your table, and then you see here the third column, ranked variable, which test to use. This is the Kruskal-Wallis test to use. Okay? Is it with the type of experiment that you're laughing with, or?
Ja, we waren aan het opzoeken waar dat dan ligt.
Not in Belgium, I think.
Nee, in de zee.
Where does it live?
In de zee, in diepe wateren.
Ah, okay. Luckily for us. Okay. And so this is just one experiment, kind of measurements and data you could gather and which tests you could do with that. So I think this table is really helpful. It's also, if you have a data set of your own and you have to decide which test to do, this table is, I think, very helpful. And then now I will just go over the tests, how in R Studio, how you can actually perform the test and look at the results. So the first one is, if we would have two nominal variables, we would have what we call a 2 times 2 contingency table. And we use actually this one when the sample size is small. Because if you look here at the first part of the table, you can actually see, we see here exact test, 1 nominal variable, 2. But actually the chi-square test is actually the same, right? Also 1. So then which one do you need to use? Well, if the sample size is small, then you use the exact test. If the sample size is large, then it's better to use the chi-square test. That's, let's say, the general rule or advice. An example for this one is you have a certain drug, a treatment with a drug, here, drug X and Y, and then you just calculate how many patients are cured, how many patients are not cured. And then you are asked, are the results statistically significant or not? Is there a distinction or not? So then this is actually how you can do that. We combine 45 and 19 here. Why a column? Because this is a vector that we create, which will be a column in our data frame. And then the second column in our data frame will be the not cured, 55, 89. If we want to make sure that this is in a data frame, I call my data frame outcome. I call here data frame. This is first vector, first column, second vector, second column. And if we want to look at the data, it's nice that you also have row names. So I immediately add here in my data frame, the row names are drug X and drug Y. And then the test is actually simple in R. That's what I found great. The most difficult thing is to choose the correct test. That's the most difficult thing. And this table helps you with that. It's just Fisher.test and then the data frame outcome in this case. This will be what you get if you do this in your R Studio. And then you will see here your p-value. So what is the result? So it is the scientific notation. This is what it is, actually 0.000 and so on. So this is obviously highly significant in this case. So you see, quite easy. And this is then a second example where you have dieting, non-dieting patients and you want to look at the difference between men and women, for example. And then this is the result. And then the student t-test is another example. Here. So this is a one sample t-test. The experiment is to look at a correlation of transferrin which is labeled red and labeled green. And then your null hypothesis is shown here and your alternative hypothesis. We are looking at the mean if it is 0 or not. So then you can actually calculate the correlation coefficients here. So this is what we add. And these are the 5 measurements we did. So 5 measurements. We put that in a vector. You can calculate the mean, for example. This is actually the mean. And then we want to know if it is significant or not with a t-test. So the one sample t-test tells us that indeed p-value is lower than 0.01, that it is significant, so we can reject our null hypothesis in this case, and this means there is colocalization of these two. And then it's the same with the two sample t-test. In this case, we again have measurements, but now we have a second group. So in this case, this you could compare with the previous example, but now we also have students of 2018, so two series. And then the null hypothesis, the mean height in two classes are the same, while the alternative hypothesis is that the mean heights in the two classes are not the same. So in this case, it's not a one sample, but a two sample t-test. And then we see in this case that the p-value is not significant. So there is actually not a difference in the mean heights between the two classes, the class of 2017 and those of 2018. So that's for the one and two sample t-test. Then the next one is the one-way ANOVA. So if you look, it's almost in the half of the page here. One-way ANOVA means you have one nominal variable and one measurement variable. And then this is a one-way analysis of variance that you do. So maybe show an example of that here. This is a plant growth data set. This is in the default data sets in R. That's why you can immediately load it. First thing I just want to do is have a look at the box plot. So actually you have a control group, we have treatment 1, and we have treatment 2. And what we want to do is see if there is a variance between these. So one thing we do is in the box plot, we use the weight here on the y-axis versus the groups. And this is control treatment 1, treatment 2. Now to do the ANOVA, we use the LM function. Again, weight versus group on our data set plant DF. And then we get this here, our plant model. You can have a look at the summary. And if you want to make analysis of variance table for this model, then you use ANOVA on this calculation here. And then you get this as output. So here your group, and then you get a p-value of 0.0159 and a star. Here you see the significance markings. This indicates that it is significant. This is just if you want also to add up or calculate the confidence interval. So this means there is a significant difference actually between these three different groups. So maybe a question, one-way ANOVA, you see nominal variable, measurement variable. What in this case is our measurement variable? What will be our measurement and what will be our nominal? Sorry? Weight is measurement indeed, and then control is one type of nominal, one category. Treatment 1 is the second, and then treatment 2 is the third one. So if you can just decide that this is a nominal, this is a measurement, look at the table and then you know which test to do. One thing what students often have a problem with, maybe I can just mention that, is this here. Because you look in your table and you say nominal. But I see a number. How can you explain this? A number, isn't that a measurement? No, it's actually a frequency that we show here. So actually it is diet, non-diet, right? So that's the label, the category. So it's not something you measure. The 10 and the 15 is indeed a number, but it is a frequency of the nominal variable. So that's sometimes why students can make a mistake in how they decide which test to do. Okay, then the next one is the Kruskal-Wallis test. So this is at the bottom then we have one test of each group, you could say, or part of the table. So then you look actually in the last column with the ranked variables. So there are two possible tests with ranks. One is the Kruskal-Wallis test that I'll show you now. This also means it is compared with a nominal variable. What is the case? This is actually a study of 2010. They observed the dogs in Rome and they made a ranking of how dominant they are. So this is the most dominant dog, were little, second one, and so on until dog 27. So this is our ranked variable. Then what is our nominal variable in this case, do you think? What will be the nominal variable? Sorry?
The sex of the dog.
Yes, the sex of the dogs. Yes, male, female is indeed. Yeah. You also see the dog name, but that's just to identify the sample or species. Of course, the dog. That's not actually a variable that we will use. So sex or gender and rank are the two variables that we take into consideration here. So this is also in one of the R datasets, dogs Scafazzo 2010. You load it with separator sign comma, so it's comma separated CSV. The header is true, so there's also a header. This is just to calculate the mean ranks. So you would see that the mean ranks for the males is 11. The mean ranks for the females is 17. This might already give you an idea if you can expect it to be significant or not. But actually just looking at the table you probably already get an idea. Last here are females and the top are males, so probably my feeling is it will be significant. But you have to do the test to be sure. So the null hypothesis, the mean ranks of the groups are the same, and it is not the same in the alternative. You do the Kruskal-test between the rank and the sex of the dogs, and then indeed you see 0.03, it is significant. So indeed there's a difference between the ranking and then the dominance between the dogs. So the males are obviously more dominant in this study. So that's the first chapter, I think. Then it's our exercises to test this, so similar exercises. And then here, based on the examples here, you should be able to decide and also help with the table which test to do. So this is the first one, second one, and that's it. Okay? So I know it's quite a lot, these tests, but I would say for each one, have a look at the table, make sure that using the table you understand the data and you are sure that, okay, based on this table, I know that it's this test to use. Okay? Then let's switch to the next one, the 7. Let me have a look. I'm still recording, yes. This is again the overview table. So the green ones are actually what we already discussed now. This is then the rest of the table. So we talked about one with a ranked variable. And then these are the other ones that I showed you an example. So let's continue with the rest of the tests. First of all, here you actually see that these are the same kind of tests. We call it an exact test, but goodness of fit. It's the same kind of test, chi-squared and G test, but the difference is between the goodness of fit and the test of independence, 1 or 2 nominal variables. And this is actually what the first few slides are about. Goodness of fit tests are used on one variable to determine whether a set of frequencies, in this case, in this example, is similar to or fits with the hypothesized frequencies, what you expect. While the test of independence are used on 2 variables to determine whether or not the first variable is related to, or then, because it's test of independence, it is independent of the second variable. So that's the difference between those two, but you can it's also the exact test and the chi-square test. And what was again the difference? When will you choose the exact test? When you will choose the chi-square test?
Exact when sample size is small and
Yes.
chi-square.
Yes, indeed. So you look at the sample size to choose one of those. Yeah. So in this case, sample size is small. The example is Mendelian inheritance here, and then you use binom.test to see, and this is actually what you expect here in this case. So you expect 1/4 to be dwarf, 3/4 of the plots to be giant, and this is actually what we enter here. So it could also be, of course, 50-50. And in this case, you see a p-value of 0.38, so definitely not significant, so we do not reject the null hypothesis. And then this is another example. If you compare with this one, it's similar, but now you see the sample sizes are much larger. So over 1,000 in this case. So that's why now here we use the chi-square test. So in this case, we look at cross bills, the tip of the upper bill here, on which side actually it is. What you would expect is that there's not really a distinction, so it's 50-50. Half of the birds will have it on the right, half of the birds would have it on the left. That is what you expect. But what is the observation? 1752 right build versus 1895. You do your test, and what you see is a p-value, so shown here, this is your result, a p-value of 0.017, so this is lower than if we use an alpha of 0.05. Significant means we can reject the null hypothesis that it's 50-50, which means if we look here, this is higher, there are significantly more left-billed cross-bills in this case. That's the result of the test. There's a small difference between chi-square and g-test, that the g values that you get are additive, but in most cases you will just use chi-square or the exact test. And to show you, I think, also for the g-test you need to install another library, while chi-square is already available. And in the example you will see that actually it is similar to the chi-square value. You see? Very, very similar. But so you choose exact test or chi-square test. And then this is an example with 2. So again here, a vaccination in the thigh or in the arm, and then what is the reaction? Is it not severe or is it a severe reaction? And then what tests should you do? Why in this case the chi-square test? First of all, chi-square test, because we have 2 nominals again. And then why the chi-square and not the Fisher? Because these values, these sample sizes in this case are very large. And then one with 3 nominal variables, that's what they call the Mantel-Haensel test. So actually, this is what you use if you have a meta-analysis. Maybe to show you the example, if you would only look at the first 2 rows here, it's like the previous example. You just have a treatment, either myosin and a placebo, and then you look at revascularization or not. So this would be one of the previous tests. But in this case, they have a meta-analysis, they actually have 5 studies. So in this case, it means the study is our 3rd nominal variable. And then you look at the table, 3 nominal variables, so that's the Mantel-Haensel test in this case. So that you see here, 3 nominals, niacin placebo is the first one, revascularization or not is the second one, and then the study is actually the 3rd one for this example. And actually the most difficult part about this is the preparation of the data. Because you have to use a 3-dimensional contingency table. So not a 2-dimensional table, but a 3rd one. And that's actually maybe, if you have to do this the first time, a bit difficult to look at. because the test itself is not that difficult. It's just Monko-Hein.test, and that's it. So let me just explain how you have to construct this table. These values here are shown here. Right? So our 2 times 2 contingency table is actually what we put here. To make it easier, I just showed you here, this is actually the data of the first study, then this is the data of the second study, the one of the third study, and so on. And now what we say is, okay, this is an array with our data points. You have to put this in 3 dimensions. So 2 times 2 here. And then I have a third dimension. 1, 2, 3, 4, 5. Okay? And then if you want to have a look at it, you can also have set the dimensions names. So then this is the first one, treatment, the 2 nominals. The revascularization, the 2 nominal values, yes and no. And then this is the study, this one. And if you construct it like this, you can directly use this array here. This is just to have a look then how RStudio constructs this. Then you can perform the test. So this is how it looks like if you print the niacin array. See here, 2 times 2 table, second, so the third dimension is then the second table and the third table. So for each study you will get actually a table. You should see how they have a table and then you have another table after that and another table after that and another table after that. That's actually then your third one. And then here you see the result of the test. Again, with here your p-value, so significant in this case. Okay, so that was the Monko-Hein test. Now we finished all these tests about 1, 2, or 3 nominal variables. So now we'll switch over to these here. We already saw in the previous chapter the one-way ANOVA. So now I'll switch over to the Tukey-Kramer test. So a Tukey-Kramer test is actually a test that you do after your one-way ANOVA. So if you would look here in your table, you see a one-way ANOVA, 1 nominal, 1 measurement. And then you just see below why Tukey-Kramer test, it's exactly the same. 1 nominal, 1 measurement. This is actually why. If you remember, I did the one-way ANOVA on the plant growth dataset. And I created this box plot here, and we knew that it was significant. But if you look at the dataset, you see that there's not that big difference, for example, between control and treatment 1. Right? So you know the overall result is significant. But what you want to do with the Tukey-Kramer test is see if there's a difference between the different conditions. So what you will actually do is we will compare treatment 1 with control, treatment 2 with control, and you will compare treatment 2 with treatment 1. This is actually what you will do with this test. So it says here, you test pairwise comparisons between them. This is actually what you do, and that is why we call it a post hoc test. So a test that you do after, in this case, the one-way ANOVA. And actually the code is quite simple. It's just like this, Tukey HSD of the ANOVA. So again, on our plant growth data set, this is what we did previously, this part. And then this is the new part here, where we do our test. And then this is actually the result of the Tukey-Kramer test. And this is important to look at. Here you see actually the pairwise comparison. So if you compare control group with treatment 1, you get an adjusted p-value of 0.39. Is this significant? No. You compare control group with treatment 2. Adjusted p-value 0.197. Significant? No. You compare treatment 1 with treatment 2, 0.012. Significant? Yes. Not highly significant, but significant. And this is actually why if we did the one-way ANOVA, it gave as a result, it is insignificant, the test. But actually, the significant differences between these two treatments, not compared to the control group. And this is actually more or less what you can see here. You see a big difference here between these two box plots, right? That's why it is significant, but not here. So it's always a good idea if you do a one-way ANOVA to also do this kind of test afterwards. Because then you can decide where actually it is. And best situation would be that all comparisons, of course, are significant, but this is not the case here. So it's important to also do this test after the one-way ANOVA test. And maybe just to tell you, you have p-values, but in this case we are talking about adjusted p-values. So when you do a series of tests, then you actually compare the means of multiple groups, and that is why then you get what we call an adjusted p-value. And you have several ways you can calculate this, several ways of getting these adjusted p-values. In this case, for example, the Tucky range is 1, but maybe you've heard probably of these here, false discovery rate, maybe you've heard of that, or also Benjamin-Hochberg. No, it doesn't ring a bell. And another one is Bonferronis adjustment, that's another one. Okay. Maybe you already had results or you read a paper and they were talking about these. So when we're talking about these adjusted p-values, you might have come to see these in these papers. But in this case then, it's the first one for the Tucky-Kramer. Okay, and then something about homoscedasticity and heteroscedasticity is by looking at the homogeneity of the variance in the data. So if the data have the same standard deviation or the same scatter, and you can do that by plotting this. And I think it's clear, this is more or less on a line, so it's similar, the same scatter, while this is not the case here. Right? And you can also test this in RStudio. And the Bartle's test is actually the most popular test to have a look at this. And that is shown here then, for the plant growth test, if you want to know. Then you get a p-value here, 0.23. So it is not significant, which actually means, in this case, homoscedasticity. So there is actually no evidence to suggest that the variance in the plant growth is different between the three treatment groups. If it would have been significant, it could be that there's actually a variance in the plant growth between the different groups. But this is not the case here. So now we know we are dealing with this kind of data. Okay. Still a couple of more tests to go over. Unfortunately. I know it's not an easy part, this part. I think this part is the most difficult of the three contact modes, I think. So the first part, I think, hopefully is the introduction of visualizing data. It's nice to use and to play with. And you can also use that on your own data set. And then also the last part, I think it's very interesting, but yeah, that is also part statistical testing of R. And if you deal with data, these are the kinds of tests, of course, that you have to do. And that reminds me, because I was talking about your project, maybe I can first tell you this. So I think, yeah, it's here at the bottom. So the test actually counts for 25% of the total score. So it can be a good idea to now already, if you still have to perform visualization, try a few things out, to also already try that on your data set you want to use for your project. That's a good way of practicing, and then you can already use these results in your project actually. Okay, so that you don't do everything in the last week, let's say. So I would advise you to, maybe by next week, you can just send me an email which data set you want to use, and then I can say that's a good one to use, and then you can already try to load it into RStudio and to different visualization techniques, and maybe a test to already do that within R on your own data set. Just by copying the code of the examples and applying it actually on your own data set. I don't know, I thought I had the links here somewhere. It's probably on the assignment, I think. Yes. So you go to assignments, there you can actually find more information. So there are a few conditions for the data set. I think you should have enough variables, so columns in the data set, and of course a number of rows, samples. So that's important. And then also, don't pay too much attention about this here, 150 lines of code. At the end, I will show you how to do this in R Markdown. There you will have comments and documentation, so then you will easily get at these lines of code. So don't be frightened by this part here. The most important thing is that you have at least 4 different blocks of code. So for example, you could have maybe box plots that you visualize, then another visualization technique, maybe then a statistical test. So you should have at least 4 different parts of dealing with the data. And you can use any technique, anything that is described in the chapters. That's actually the goal. That's the best way to practice. Then of course, where can I find a data set, right? Actually, lots of the data sets that are being used in this course come from this resource. So you can just go to that one. It's just an HTML page. And at first, maybe I can already show you. The first one here already tells you the package. So it means if you just install this package, for example, boot, you will immediately have access to all these data sets. You scroll down, and maybe you see, so you see there are quite a lot of different data sets. So for example, maybe you want to use this one, this package, then you see other types of data. What is it about? Rows and columns, I think this is. And then at the end, also important, 2 columns is, this one is the data. If you still already want to have a look at it, but it's easier to install the package and load it directly. And this is then the documentation. Also interesting, because there you already get the description of the different variables. And in some cases also a link or a reference to a publication, where you can maybe have some more information. But in this case, 1, 2, 3, 4 different kinds of variables. And if you want to search, it's good to not only have a data set with nominals or a data set with measurements. It's actually best if you have a combination of both, because then you can try out different visualization techniques. Okay? This is one resource where you can look for data sets. Another one is Kaggle. And a third one, also in Google, they actually have a dataset search where you can look at. But I think most of the students of the day program actually looked at these 2 first resources to get their publicly available data to use in their project. Any questions about this?
I don't see what we have to do with it, and you have to perform some tests, but what's the outcome? What do you expect from us?
Okay, so first thing is you choose your data set. Okay, something you find interesting. Make sure you have a couple of variables that you can use, and then in the chapter of visualization you saw if I have, for example, 2 measurements, I can make a scatter plot. Or if I have these kind of variables, I can make box plots. And that is what you do with the data. You load it in and you represent it. You provide a title, you label the axis, maybe change the axis, provide a legend, color. If you have different groups of samples, you color, playing actually with the data, applying what you've learned during the course. That's actually what you have to do.
But then you have like a lot of plots and stuff all together, but...
No, that's actually what is one block. So if you choose, for example, 2 types of variables, you select something to visualize, of course not 4 times a box plot. That's not the intention. Maybe a box plot, and then maybe a bubble chart, maybe something else. If it's a big data set, you can try MDS or PCA, multidimensional scaling, for example. Yeah. Or also what some students do is they just look at another visualization technique. There are also other ones that are not available or described in the course. It's just actually installing a new package and just having a look at the information and the help and applying that one. Yeah, that's also possible. It's just actually applying what you've learned on a real data set. That's the best way to practice. And then at the end you provide that in a report, but that I'll explain in the third contact moment. You can just now try it out in your R code, and then the last step will be just copying it into what we call R Markdown. But that's for next time that I'll explain. Now, if you can now just what you used during the example code and during the exercises, already try that out on your data set that you choose. That's already a good preparation then for the last 2 weeks to prepare your R Markdown, and that I'll explain then. Yeah. Okay. We are all awake again, so good to start the last series of tests. Okay. And so let me have a look again. Yes, the nested ANOVA. So that is one measurement variable and then more than one nominal variable. But the nominal variables are nested in this case. And actually this is just informative. It's just to tell you how you can do it, but you should not be able to perform it. Okay? So only limit to what I provide you example code. That is what I might ask also on the exam. It's just to inform you of this kind of data set, then this is that kind of test that you could do. So in this case, we'll have nominals are our groups, technicians Brad and Janet. They did an experiment and they measured the protein uptake. So these are all their measurements. But you can already see here that we have a second nominal, a subgroup. Because Brad, he measured rat Arnold, Ben and Charlie, and then Janet measured the rats Dave, Eddie and Frank. So these are then actually nominal subgroups. So if you look at the nested ANOVA, 2 in this case or more are our nominal variables. And then you see one measurement variable, the protein uptake. So this would be the kind of testing that you could do. A two-way ANOVA is actually where you can also look at an interaction. So you have one measurement variable, this would then be the Y here, and then you have two nominal variables, in this case the A and the B. Now we can actually use the same function as we did with the one-way ANOVA. So remember, use the LM, you can also use the AOV. But there's a difference between these two. You can have a look if there is an effect without interaction, then you use this here to describe. I'll explain the code immediately. Or the other way is you also do factor crossing. So why do you write it like this? The same plus, but also look at the interaction. Meaning if there is an interaction between the two nominal variables. If you want to rewrite this, it's easier to write this just with the asterisk, with the star. So this is just actually the same. You can use both. And that is what you will see in the example code. Here. So in this case, I've used the interaction. We have our activity, shown here, measurement. And then these are our two nominal variables. So one is our genotype. So in this case, we have 3, FF, FS, SS. And then the second nominal is female, male. Okay? And we can also use that in a box plot. So normally we did previously this for a box plot, but you can also use this, and then you nicely see here genotype times 6, and then you see genotype female, second genotype female, third genotype female, and then the same repeated for the males. Okay, so this is a way you can get a box plot like this with actually 3. So 2 nominals, 1 measurement. And this is actually how the data looks like. To refresh your memory, this is what we did with the plant model. So we use this ln function, weight versus group. How do we do it with the 2A ANOVA? It's the same. But now here we don't use 1 nominal, but we use 2 nominals here. And for the rest, it's actually quite similar. And then ANOVA, and then here you get probability values again. And then you can distinguish are they significant or not. So you can see here actually there is no effect of sex, 0.77, no effect of genotype, 0.84, and also there is no significant effect of both. So there is no interaction because those combined is 0.6. So you actually get these 3 values in this case. Why? Because this is the short annotation with the star. Whenever we have a look back, actually if you use that full, so you look at A, you look at B, and you look at the combination, the interaction factor crossing. So this is why you get these 3 values. Okay, and then the paired t-test. So this is also 1 measurement, 2 nominals, but we look at pairs of observations in this case. This is where the distinction is with the previous ones. Maybe the best way to show you is to show it with the data set itself. So here you see that actually you have always 1 pair of observation. So bird 1, these 2 measurements. Bird 2, these 2 measurements. Bird 3, these 2 measurements. So these are always what we call pairs of observations. This is why we do a paired t-test. While if we look at our 2A ANOVA, so it's the same data, 2 nominals, 1 measurement, but here you see, for example, male FF, we get a measurement, okay? So we get here 2 already. So not only the pairs of observation, that is actually what is the major difference between these 2. So what is the experiment here? They did in 2002, they actually had a look at the feathers. Well, there apparently was 1 odd feather, different. And then they looked at the yellowness of the feather of these birds. And this is what then they measured here for each bird. The typical feather, they measured the yellowness, and they measured the yellowness and the odd feather. And then they did a paired t-test in this case. So this is the t.test, and then our 2 vectors. So the column typical feather, the column odd feather. So it's actually just this one here and this one that we use in our t-test. And then we see again p-value 0.001. So in this case significant, so we can reject the null hypothesis in this case. Okay, so hopefully, I know I only have 2 hours to explain. I can't explain it in too much detail, but I'll try to give you each time the major distinguishes between the differences between the different tests, how you can decide if you would have a new data set, how you can decide which test to use. So first use the table, and then if you have certain tests that are similar, based on the examples, I think it should be doable to decide which test to use, hopefully. Right? The more you practice, actually, the better you get at this. Okay, the next one is the Wilcoxon signed rank test. So also multiple pairs of observation. So again, this is exactly the same as the paired t-test. Then where is the difference between Wilcoxon signed rank test and the paired t-test is how you have the data. So in most cases you assume that the data is normally distributed, but in the example I'll show you now this is not the case. And that is why if you have non-parametric test you have to do, if the data is not normally distributed in this case, then you have to use the Wilkinson-Saint rank test instead of the pairs t-test. And this is why I also show here the histograms to show that to you. Because actually, if you look at the data, one thing that you probably notice is here the last one, that this is an outlier. You see this is much larger than the rest. And this actually disturbs the distribution of the data here. So this means the data is not normally distributed, and that is why you should not do a paired t-test, but you should do this kind of test. Because you see pair of observation, pairs of observation, pairs of observation. So for each one, each clone in this case, you have one pair of observation. So you might say, oh, I will do a pair t-test. No, you see here, and that's a good idea to look at the distribution here, to say, no, it's not a pair t-test that I should use, but I should use a Wilkinson-Saint rank test in this case. How would you do that in RStudio? With Wilcox.test. To show you the difference, I also did a normal t-test, and actually the difference is not that big in this case. So the outcome would actually be the same. Conclusion also, so similar p-value, conclusion the same, but just by looking at the distribution and looking at the data, the better and safer way would be to use this test in this case instead of the paired t-test. So that is the difference between these tests. And then again some exercises to try out. So I'll wait until next week to publish these. So if you have difficulties to decide which test to use, try to have a look which data, maybe compare with the examples what you think is, and then try the test and make a conclusion, and then you can compare it with the results with the example, the solution next week. Okay? So on time I think. And then the last series. So this is statistical testing 3. Just have a look if I'm still recording everything. Yes. Now the last one, so we already discussed quite some tests, and this is actually what we still have to do. This is even more advanced, so you don't have to, I will not ask you to perform these tests. It's just informative that I want to show them to you. So linear regression correlation is important that you can do the ANCOVA and the Spearman rank correlation in this case. But I will not ask these for you to do. Okay? So not a multiple regression, simple and logistic, and a multiple logistic. I might only ask you linear correlation, ANCOVA, and Spearman. Okay. This is just a cartoon that you can find on XKCD. If you would plot data and you would try to see something in the data. These are things you can do. This is actually linear modeling here. But you can see you can do much more, even strange things like this. But actually, there's nothing in this data. If you just look, it's randomly scattered, right? So they say sometimes if you torture the data long enough, it will confess to everything or anything. There's nothing in this data set. It's just random scattering, okay? So just by looking at the data, hopefully you're convinced that there's nothing to see, right? Although this is quite nice, of course, something like that, or even this might get people convinced, or this, but there's nothing in the data. Okay, so correlation and regression is it actually we have one measurement variable and we want to know if it is associated with another one, with another measurement variable. So these are two examples. Drug dosage, blood pressure could be one, mice body length and offspring could be another one, for example. So what we then do in R is determine the correlation. And it can be three different outcomes. If there is no pattern, there is actually between the two variables, there is obviously no correlation. So this then would be the 0. Or it can be, if one variable is increasing, what you will see that the other measurement variable is also increasing, the same. So now we are talking about positively correlated. But it's also possible if one variable increases, that the other one is the opposite and it decreases. In this case, we say we have negative correlation. So that's the correlation, then the regression. You can try to make a linear equation and then draw, like here, oh sorry, other way. Here, try to draw a line through the data points, right? So this is what you do with linear regression. This is one kind of equation then that you have to determine. So in this case then we determine the intercept and the slope. I'll come back to that in one of the next slides. And you can do more advanced equations, polynomial regression in this case. You might already have noticed that we also use here the same in R, the LM function that we've used previously. You can also use those LM functions for these, for linear and for polynomial regression. In most cases, I think this will be sufficient. And in biology, I think this is, you can have other types of equations, but probably that will not be the case. So I think this sums what you will probably have to use on real data sets. This is then an example to fit linear regression model as an example. Again, the LM, here our population, and then for example, a year could be one fit that you want to do. If you want to do more a polynomial regression, then you have to write something like this, a kind of complex equation that you have to make. So maybe show again an example on our iris flower data set. So in this case, we'll use the petal length and the sepal length of our iris flowers. And what we want to do is want to see if there is a correlation or not. If the value would be 0, this means there is no correlation. Positive correlation, so if one increases, the other one increases, this would mean the value is higher than 0, close to 1, for example. If it is a negative correlation, it could be lower than 0, close to -1 in this case. And if we try it out on petal length, sepal length, and our iris data flowers, and we do the correlation, then you will see here, of course, petal length in this case is perfect because it's the same. But we're actually interested in the difference between petal and sepal. You see 0.87, so that's quite high. So I would suggest, or I would expect this to be a positive correlation. And indeed, if you look at the result, you will see that it's a highly significant p-value in this case. There are again different methods to do this, and in this case, for example, you could use what they call the Pearson coefficient. So this is one way to do that. And then of course, if it is significant, here in this case, it's also always nice to also visualize that you can see that it's significant, that it's not like here. So if you would do that here, normally the result will be that it is not significant. And hopefully I can convince you that here there is a trend, that there is a correlation. Right? If this data point here, if the petal length is low here, you also see that the sepal length is low. While if in this case you have a very high petal length, for that data point you also see that the sepal length is very high. So that is what the positive correlation is referring to. Right? Another one, let's say the petal length is average here, that means that also the sepal length is averaged. So you see that there is a trend. There's indeed, you can model this and see that the data points are in this range and not just randomly as in the comic, right? And this is then to show you the plot. So that from the previous chapter, the only thing actually that you have to do is add the red line, what we call the regression line. And you can directly use this here if you have here your linear model. The only thing you have to do is use add line to add after the plot. You add your line here, and you can just add an extra parameter. For example, I will color it in red. And then indeed I see here a red line showing my model, my equation then. And then you can do some other more plots like this. I will not go into too much detail, and there's a bit of explanation here for you accompanied with these plots. So that was the regression and the correlation. Then the analysis of covariance or uncova. So this is actually similar as the previous example, but now we want to compare two or more regression lines. And in the example, I will only compare two regression lines. And I already talked about the slope and intercept. And this is now also important. Remember the formula that I showed you here? These are actually these two values. This is what we call the slope value, and then this is what we call the intercept value. And with these two values, you have your formula, and you can actually draw your line here. So then this would be 0, 1 at this point. You know your slope, and then you can actually draw your line. Now this is this formula that I talked about in the beginning. So shown again here, equation of the regression line. Your A and your B value are what we call intercept and slope value. What is the data set that I want to use? This one here. Two crickets, I think. So they make quite a lot of noise if they use their wings. And actually they measured this in already 1962. They actually measured this during the mating song of the male crickets. So they examined this in the male crickets. Two species. This is one type of male cricket, and this is the other species. And they want to see what happens if you would actually increase or play with the temperature. This is actually the experiment, what you see here. So this is one species, this is another species, so obviously this is a nominal variable. And then these are our two measurement variables. The one is the temperature that you see here, and that, for example, this temperature, these are the pulses per second of the wings of this cricket. And then this is the same. This is actually the data that we'll use, and then I've already, so this is from the publication, and this is then how we will use it in our studio. If you know the data set, I've just abbreviated the species with the two letters here. So OE and the ON in the data set. So this should by now be familiar. You load the data set, you use the ANOVA here with this formula. So this is the long version, remember, plus and then the column, but you could also use temp star species, of course. And then what is the result? That it is significant. So both temperature and species have a significant effect on the pulses per second, but the interaction is not significant. How do I know that? Here, temperature is highly significant, species highly significant, but there is no interaction between the two, because this is not significant. What do we want to do now is we want to compare and have a look at both regression lines. Okay? And this is actually quite a nice example. I think if you look at them, these two regression lines, you see the data points here for one species, and these are in black. So red data points for one species, black data points for another species. If you make your equation here and you draw the line, you actually see that they are exactly the same. They are parallel. Agree? Yes? This is actually what you want to have a look at now. Yeah. So just maybe tell you that this is model 1. This is actually without the interaction. Okay, so with the interaction, sorry. And then the second model here is without the interaction. So only the plus, not with the colon or with the star. So without the interaction. This is the difference between what I call M1 and M2. I can ask for the summary then. If you want to compare the models, then this is what you do. Again, ANOVA, and then you just add the two models to compare them. And then you have to do this here actually to calculate these lines. So these are the coefficients, intercept and slope. And then this is how you can get them for the two species and then add actually the lines here. So if you then calculate this, then you actually have your black line here, and then you can also add your red line as a result. Okay? And then I think the last one, then the next is even more advanced, but that is just informative. This is the last one I hope that you can use or would be able to make on the exam, the Spearman-Ryan correlation. So we already did one. Remember the Kruskal-Wallis test with the dogs in Rome? That was the previous example. Now we will use two rank variables. What is the experiment they did? Now not with dogs, but with monkeys. And so they actually ranked the monkeys, also again the dominance of the monkeys. So this is our first ranked variable. And the second one is a bit strange maybe. The second one is actually, they wanted to see if you would have a more dominant monkey, if there is a difference in their, the number of grams of nematode X in their species. Okay? So you could also rank that. And that is what you see here. This is the name of the monkey, so 6. This is the dominance rank, 1 to 6. The most dominant one is Errol, the least is Hope. And then they have here the X per gram, and based on that, of course, you can make your rank value. So this is actually a measurement, but this then you can, of course, rank. So I think it's already obvious. What you see is that the most dominant monkey has actually the most X per gram in his species. Only, I think here, there's a switch, but the top 4 is exactly the rank is the same. So what test do you have to do with is called the Spearman-Rank correlation. So the R-core, it's not default available in R. So what you will have to do is you will have to install this package, this library. And then you should be able to do the test. And in this case, the outcome is that the p-value is significant. And that is actually what we expected, that there is actually a correlation, what you can already see here, between the two ranked variables. Right? Okay, so that is a quick description of all the tests. If you would want more information or something is unclear, don't hesitate to send a mail. I know that this is a difficult part, so don't hesitate to mail me if you have a question about this. And then just informative, the last part. So then you can go a step further, you can have a look at multiple regression, then you can get like these even more difficult equations. Then this again, which hypothesis you would have in that case, and then how you have to model that in this case. This is the example then of the data. These are then the columns that we use, and then actually this is the outcome of your correlation. So this is maybe nice to show you. In this case, you could already see between all these variables that we have, you can also have a look at the correlation. And then you can immediately see, for example, this value is close to 0, so there probably will not be a correlation between DO2 and max depth. But then on the other hand, I know maybe this one, temperature and DO2, there might be a correlation minus 0.3. Yeah, and also see acreage and long nose. So you can actually visualize it with the pairwise plot. So that's a really nice one to immediately see if there is a correlation or not. You can plot all of the data. This is one example, and even a better one is this one. So you can do exactly the same with this library, but this gives you even more information. Why? You get here with an equation that's calculated, like I showed you in the cartoon. It already draws here the lines. It already gives you here pairwise each time a histogram. So you can see that this is quite normally distributed, while this is not the case, for example. And here you can actually already see how the correlation is. Okay, so indeed 0.3 here, 0.35 and so on. Well, there is clearly no correlation here. So this is also a really nice one if you're dealing with several of these variables that you measured, to use this package and make one large correlation chart, let's say, with lots of information in it. Okay, I will not go into much detail of this here. If you are interested in it, you can have a look at the slides. That will take us too far, I think. If you can already do the previous tests, I think I'm very happy with that. Okay, then I'll stop for now with my explanation, and then if you would have any questions, I can answer them right now.
It might be a stupid question, but in the RStudio, in one of the first presentations, you talk about the BIT package.
Yes.
It always says like it's deprecated. I should use BIT Manager or something.
Yes, that was a source where you can also find packages, but we will not use them in here. Packages of that you might use in high throughput analysis or in one of the other courses, and then at the time we can have a look how to do that. It's just another resource, yeah, indeed. It changes fast, so packages get updated also. So then at that time we will look which package to use and how you can use that in your RStudio. Now, any other questions? Blown away by the tests, I guess.
Moeten wij ons dataset doorsturen? Dat je zei daarnet?
You can just send me an email with a link, maybe the name of the dataset and just the link then, and then I'll just have a quick look at it. I will just check actually rows and columns and the type of variables. If you only have 4 columns and they are all numerical measurements, or they would be all the 4 columns would be nominal, then we'll probably say no. But if you would have maybe 5, 6, 7 and there is 1 or 2 nominal measurements or the other way around, then it will be no problem to use it. And of course, the larger the data sets, the nicer you can play with it, I guess. Not too huge, but...
Dat ik er denk ik in gevonden had en anders stuur ik je de link.
Okay, all I can show you now. If there are no more questions, then I will stop the recording, and then you can already show the data set, and I can already tell you if it's okay or not. Okay? So there are no other questions for now? No? Okay. Then I will stop here. And then, always exciting, if it is still broadcasting the live stream. Still alive. Yes. Okay.
Dat is een dataset met 1000 en zoveel.